Hello everyone, welcome back to the channel. In this video, I am going to start with the DC machine. DC stands for direct current, and a machine can be a generator or it can be a motor. So DC machine can act as motor or it can act as motor depending upon which supply we are giving to the machine. In this video, I will discuss the construction of DC machine as well as their working principle. Now for generator, the input is mechanical energy and output is electrical energy. While it's vice versa in case of motor, where input is electrical energy and output is mechanical energy. So same machine can work as DC generator and it can work as DC motor depending upon which supply we are giving to the machine. So if we have to say what is a generator, so generator is that machine which converts a mechanical energy into electrical energy, and motor is that machine which changes the electrical energy into mechanical energy, and we can use that mechanical energy to drive some different load. The basic principle of all generators, irrespective whether they are DC or AC, is same, and that is, for a generator we need a conductor and magnetic field, and either of these two, one should be rotating and other should be stationary. So it means third thing which we need over here, that is mechanical energy for movement. So either the conductor should be stationary or magnetic field and one should be rotating. So when one is stationary, other one is rotating, it means there is flux cut by the conductor. So whenever there is flux cut by the conductor, there is an induced EMF in that conductor, and that can be collected from the generator in the form of electrical energy. While for motor, we need again conductor and magnetic field, and instead of mechanical energy, now we need the electrical energy, since the principle of motor is that when a current carrying conductor is placed inside the magnetic field, then it will experience a force, and that force will lead to torque and motor starts rotating. So the basic principle of all motors is same. Also, we need to know that most of the DC machines, they are similar to AC machines since they have same AC voltages and currents within them. Now the question is that how they are different from the AC machines. Why we are saying that these are the direct current machines? So direct current machines have DC output because they have a mechanism of converting the AC to DC at their terminals, and that mechanism is known as commutating action, which is achieved through commutator. So commutator is the one part of the DC machine which differentiates it from the rest of the AC machines. So if we talk about the generators, the DC generators are not common, or we say that they are rarely used because we can easily avail the DC supply through the electronic rectifiers. With the advancement in the power electronic devices, we have the converters available in different sizes, and we can easily avail the DC supply from the AC only. While the motors are widely used, they are commonly used in the automobiles, in the aircrafts, or in portable electronic devices. And in addition to this, these are used in the applications where we need to control the speed over a wide range. Now, coming to the construction, that how a DC motor looks like. So, before moving on to this, what we have seen, that one thing should be rotating in generator, and in case of motor, because of these three things, we have a rotation. So, machine, whether it's a motor or generator, it will have two parts. One is stator, which is actually stationary part, and second part is rotor, which is free to rotate. And instead of permanent magnets, to produce the magnetic field, we use electromagnets in case of DC machines. The electromagnets have certain advantages over the permanent magnets. We can easily control the magnetic field. They don't lose the magnetism with time. Also, they are more cost effective when the size of machine is large in comparison to the permanent magnets. So that's why we go for the electromagnets. For electromagnets, we actually need to use field winding, which is always supplied from a DC source. So though we say that in case of generator, we have the mechanical energy as input and electrical energy is input in case of motor, but field is always supplied from the DC source, irrespective whether it's motor or generator, since we need to produce a magnetic field in the machine. So we have stator and rotor, and in case of DC machines, the field winding is always placed on the stator, and on rotor we have the conductors, which will lead to actually armature winding. So in armature winding, there is an induced EMF in case of generator. And in case of motor, we will give the supply to this armature winding, and I will discuss this in this video only. So moving on to the construction, this is how a DC motor stator looks like. So we have the outer frame or the motor house or the generator house. From outside, it looks like this only. These are the wires which are available to us at the terminal box for connections to the supply. And what we see over here, this over here, here, and here, these are the field windings which are placed on the salient poles of the machine. So inside this motor house, we have a stator core. Can you see over here that we have a stator core like this one? This one is a stator core. This is stator core, from which we have projected poles available. Like this is a projected pole. This is also a projected pole. On these projected poles, we have the field winding. So we can show it like that core looks like this, with four different projected poles which are looking like this. So this is how it looks like. So this is known as pole shoe. Now this pole shoe has more width in comparison to this pole. There are two reasons. One is to provide the mechanical strength to the field winding. Second one is to increase the effective area for the flow of flux. So we place the winding, field winding over these like this, like it's placed over here. To provide the mechanical strength, this width is more in comparison to the pole. So DC supply is given to this field winding, and these poles will become alternatively north pole, south pole, north pole, south pole. And inside this, which is a free space, a rotor is placed. And there is a minor air gap between the stator and rotor, and this is how the rotor looks like. In rotor, we have shaft over which different parts of the machine are placed. This is the rotor core. Now, whether it's a stator core or rotor core, both are made up of thin laminations in order to reduce the eddy current loss. Now, in this rotor, the slots are available. Can you see over here? These are the cuts in which the conductors are placed. So we can say see the conductors outside over here and over here up to here. So these are the conductors which are placed in the slots available in the rotor core, and these are known as conductors, or completely it is known as armature winding. So armature winding is placed on the rotor which is free to rotate, and the ends of all these conductors, they are connected to this part which is known as commutator, which we can say it is the heart of DC machine. So what is a commutator? If you look in this, we can see like lines over here, that this is one line, second line, and then this one is a different line over here. So basically these are the different commutator segments which are stacked all together, and they are insulated from each other. The commutator segments, they are insulated from each other, and each commutator segment is connected with one of the armature conductors, as we see over here. And from these commutator segments, we will collect the supply through the brushes. So brushes are in the stator assembly, so they are actually stationary, and the commutator is rotating. So brush and commutator assembly will give us the output in the form of unidirectional waveform. So this is how they look like pictorially, and if we have to show the cut view, that how it looks like, then a 4-pole machine looks like this. So this is the base of the machine, then this is the yoke or the stator core. Here we have the projected poles. This is 1, 2, 3 and 4, and these are the field windings which are placed over here. And here we have rotor core in which we have the slots, and these are the conductors placed inside the slots. These are the conductors. These are armature conductors. So flux will follow the minimum reluctance path. So it will try to remain confined to the stator core and the rotor core. Now, to understand the working principle of motor and generator, instead of using large number of conductors and large number of poles, I will consider a 2-pole machine with one coil. So one coil means two conductors. So I will consider that one. But before moving on to the principle, we need to know one rule which is very important. It's Fleming's right hand rule. Now, according to Fleming's right hand rule, if we know the direction of force and magnetic field, then we can find out the direction of induced current. So these two are known and we can find out the direction of this induced current which is unknown to us. So this is actually applicable to generating action, since in case of generator we know the direction of magnetic field and direction of rotation, and we need to find out the direction of induced current. Similarly, we have Fleming's left hand rule which is applicable to motoring action. Now what is motoring action? Motoring action is when we know the direction of magnetic field and current, and we need to know the direction of force. So direction of magnetic field and current are known while direction of force is unknown, but we can find out that using Fleming's left hand rule. So this is how we can represent Fleming's rule pictorially. Thumb is giving us the direction of force, index finger gives us the direction of magnetic field, and the middle finger gives the direction of current or induced current. So left hand rule is applicable to motoring action while the right hand rule is applicable to generating action. So we must know these two rules. Now let's discuss the principle of generator. Now generator principle is, let's say we have two poles. Now instead of the electromagnets, I am just showing two poles, north pole and south pole, in which a coil is placed which has two conductors. Since we have two conductors, so we will have the commutator divided into two sections. I am showing one with filled color and second one without color. So direction of field is like this. The brushes are fixed. Let's say this is brush B1, this one is B2, and here we have resistance R. Let's say we are rotating it in anti-clockwise direction. Usually we take anti-clockwise direction as default direction. So for anti-clockwise direction, if this is conductor AB and this one is CD, conductor AB is experiencing force in downward direction while CD is experience the force in upward direction. Direction of field is known to us, direction of force is known to us. We need to find out the direction of induced current. Now, if we just look at conductor CD, which is experiencing a force in upward direction, direction of field is from left to right or from north pole to south pole. So direction of induced current will be towards the plane, or we can say it is flowing from D to C. And if we look at conductor AB, now for conductor AB, direction of field is remaining same, it is experiencing force in downward direction. So direction of induced current will be from B to A. Now you can just check the direction of these induced currents by your own by applying Fleming's right hand rule. Now what we see, since this is rotating after 180-degree, okay, I can just show that how the current is completing its path. Now current is going towards the resistance through brush B1 and returning back through B2. So this is a positive terminal, this one is the negative terminal, or this is the polarity of voltage across a load resistance. Now after 180-degree rotation, what will happen? This will be A, this will be B, C and D. Now the commutator segment, which is the shaded one, it is now connected with the brush B1. Since the brushes are fixed, so B1 is over here, B2 is over here, and here we have resistance over, we can say it's a load. This is rotating again in anti-clockwise direction. Now conductor AB is experiencing force in upward direction and CD is experiencing force in downward direction. So what we see, that AB has taken the place of CD conductor while CD conductor has taken the place of AB conductor. Now again, if we apply the Fleming's right hand rule to find out the direction of induced current, it will be from A to B in conductor AB, and for conductor CD it will be from C to D. Now if we just compare these two, here current is flowing from B to A, here current is flowing from A to B. It means there is reversal of current in the conductor. Same applies to conductor CD, but when we look at the direction of current through this resistance or the polarity of voltage across the resistance, the current is leaving the commutator segment through brush B1 and then entering back through brush B2. So this is the direction of current. It means this is positive terminal and this one is negative terminal. So what is happening inside the machine? Inside the machine, current is having alternating nature, while across the load we are getting unidirectional output. So we can show it like that the output is like this. Obviously it will have 0 one position when there is minimum flux cut by the conductor, so that will lead to 0 induced EMF, and since it is rotating, this coil is making angle with the magnetic field, so accordingly we will have the different magnitude of induced EMF. So we can say induced EMF over here, and here we can say degree of rotation on x-axis. Accordingly we have the induced EMF. So what we see inside the conductors, it's alternating, but because of the presence of the commutator segment, we are getting unidirectional output. Now this one is unidirectional, but still it's pulsating. Now if we move on back to this diagram, so we have the conductors which are all around the rotor periphery, 1, 2, 3 and so on, and they are at some angle. We can say this is the 15 degrees difference or 10 degrees difference. So obviously If induced EMF is maximum over here in this conductor or over here, then it will have some lesser value over here, lesser, then it again starts increasing. So different conductors at different instant will have different magnitude of induced EMF. So if this one is first for first coil, then it could be like this for the second, like this for the third, fourth, and then fifth, and so on. And obviously it will have in the in this direction as well. So the resultant which we get over here, that is almost constant. It's almost constant. So this is how we get a constant output across the DC generator. Now in order to increase the EMF, we connect the coils in series, or we can say to increase the voltage rating. For increasing voltage rating, we need to connect the coils in series, and for increasing current rating, the coils are connected in parallel. So we don't have like only two conductors in this. We will have multiple conductors like shown over here, and they are connected in series or in parallel according to that how much we need to increase the voltage rating and how much we need to increase the current rating. Similarly, we can discuss the principle of motor. Now for motor, we will have the same representation that we have in North Pole, South Pole. Inside that we have a coil with two conductors connected to commutator. So shaded and unshaded region. Since we have two conductors, so only two conductor segments, while actually we will have multiple conductors. Brush B1, B2, and through these brushes we will actually supply the DC voltage. So here we have DC supply. So this is a DC supply. So current will flow in this direction through brush B1. If this is A, B, C, and D. So this is how the conductor looks like. Now over here I have just copied it to show you the principle after 180-degree rotation. I will come to that also. Now if we just focus on this, now we know the direction of field. Direction of field is like this. Direction of current is also known to us, but direction of force is not known to us. Now if we focus on conductor AB, if we focus on conductor AB where current is flowing from A to B, direction of field is from north to south, or we can say from left to right. So as per the direction of current, this conductor will start experiencing a force in downward direction. And when we look at conductor CD, direction of field is same. Now current is flowing from C to D. Using Fleming's left-hand rule, we can find out the direction of field and it will come out as upward direction. Since CD is flowing, experiencing a force in upward direction, AB is experiencing it in downward direction, so it will start rotating in anti-clockwise direction. After 180 degrees, what will happen? Conductor CD is now under the influence of North Pole and AB is under the influence of South Pole. So the shaded commutator segment is now in connection with brush B1 and unshaded is with brush B2. So current through conductor CD is now flowing from D to C, and in AB it is now flowing from A to B. So this one is just opposite to what was happening in this case. Earlier current was flowing from A to B, here it's from B to A. Here it was from C to D. Now in this case is from D to C. Now again we have to find out the direction of force. Now the conductor CD, it will experience a downwards force while conductor AB will experience a upward force. You can find out the directions using Fleming's left hand rule, since Fleming's left hand rule is applicable for the motoring action, and motoring action is when we know the direction of field and direction of current, then we can find out the direction of force. So again it will try to rotate in anti-clockwise direction. Since this keeps on moving, so the motor s- starts rotating in the anti-clockwise direction. So we can reverse the direction of rotation if we just change the supply terminals. If this terminal is connected to negative and positive, obviously there is the reverse direction of flow of current through the armature, and that will lead to opposite direction of rotation. So this is how a DC motor operates. So what we see over here, in motor and generator, the commutator has the function of changing the alternating quantity to direct current quantity. The currents which are actually alternating inside the armature conductor, they have the unidirectional flow through the load or from the source. So it acts as a mechanical rectifier. While in armature, we have the induced EMF in case of generator and the armature winding that acts as current carrying conductor, which is placed inside the magnetic field in case of motor. Now, what is the magnitude of that induced EMF in case of generator, that we can find out from the EMF equation that I will discuss in the next video. Also, what we can see over here, that once the motor starts rotating, whether in this position or in this position, now conductor is rotated through a stationary magnetic field. So when conductor rotates through stationary magnetic field, so there is an induced EMF in that conductor. So induced EMF is also there in case of the motor, and that induced EMF in case of motor is known as back EMF, which we will denote by EB. So I will explain in the next video why it is known as back EMF. So if you find this content helpful for you, please do share and like the video. Thanks for watching the video.